Swayam Prabha. Digital India. Educated India.
So, welcome to our next lecture of Module 2 on some useful probability distributions. In this particular module, we are first of all going to focus on continuous distributions, that is, normal distribution and exponential distribution, and then we will talk about discrete distributions that we already specified in our last lecture. So the first and foremost distribution that comes handy in most of the situation is normal distribution, and normal distribution typically applies to continuous variables. And mathematically, functional form is written by 1 by sigma root 2 pi and exponential of minus 1 by 2x minus mu upon sigma square. Again, no need to remember this particular equation. If you use it multiple times, you would automatically remember that. But here there are few important things that we need to understand conceptually, then worrying about the mathematical form. The first thing that we should notice here is that it's an exponential function. So this is some exponential of minus of fx. What does that mean? That for much larger values of x, this would decay sharply, and that would mean that it would have thin tails. That is, probability of outliers or things far away from mean would be close to 0. Again, the square here, x minus mu upon sigma square, the square takes care of that tails on both sides, they decay exponentially. And if we go far away from the mean, probability of finding certain values of x greater than equal to those outliers practically becomes 0. Also, if you notice, it's a square function in x. That means it is symmetrical. And this indeed is symmetrical around the mean. Since this is symmetrical around the mean, density of normal distribution is maximum at mean itself. And if density is maximum at mean, that means that its mean and mode also coincide. And by virtue of symmetry, area at half point of this curve is also equal to 0.5. That means mean and mode and median for normal distribution are all same. Hence, for sake of conciseness, whenever we are talking about mean, we are implicitly talking about mode and median without mentioning it explicitly whenever we are dealing with normal distribution. But we have to understand that certain distributions may not be symmetrical, that they may be left skewed or right skewed. So we should not generalize what we learn for normal distribution to every other distribution. But normal distribution is one of the most commonly used distribution and also is known as Gaussian distribution, named after scientist mathematician Gauss, who has made fundamental contributions in world of probability and statistics and by and large mathematics. One question that is obvious at this stage is that why do we really need distributions? Why this fx form that looks mathematically so daunting comes into picture? The reason is that sometimes when we encounter lot of data, we realize that certain functional forms generalize to different kinds of data sets. And hence, instead of dealing with all those data sets separately or trying to fit new function every time, we wanted to have a generalized function that can be applied to different situations. Hence, this normal distribution can also apply to health data, for example. It can also apply to flood data. It can also apply to traffic data. So if we specify that traffic volume at a given intersection follows normal distribution, then we don't need much of a domain information that at what rate cars are coming, because we have already characterized it with a mathematical functional form, fx equal to into an exponential function of x, mu and sigma, and hence whatever properties fx would have, that would be inherited or applied directly to the data or samples under consideration. And that's why distributions are very, very powerful. And today we will see a couple of examples that how we can actually use these distributions for quantification of risk. Now, if we look into visual representation of normal distribution, here I have two plots. Let us say that this is plot A and plot B. When we focus on plot A, you see three normal distributions, all having different variance but same mean. So they all are centered around mean equal to 0, but dispersions are 1, 4 and 9. And you can clearly see that despite being at the same center, how their dispersion changes drastically from one distribution to another. And that further reinforces our point that why we need two measures to characterize any distribution fully, that is its central tendency and its dispersion around that central tendency. Similarly, when we talk about another simulation where we keep standard deviation or variance same but keep on shifting the mean, you see that these distributions with mean of -2, 0 and 2, they have drifted apart from each other and the spread around the mean remains same. Sometimes we also call this mean as scale. So location. I correct it. We call this as location of a particular distribution, and variance is sometimes referred to as scale of the distribution. So whenever you encounter words location and scale, we are essentially talking about the central tendency, and scale essentially talks about the measure of dispersion around the mean. However, in context of normal distribution, we typically call it mean variance, but when we will go to extreme value distribution, they would be called as location, scale and shape, because it would be a 3-parameter distribution. Now, here I introduced another term called as parameters. These mean and sigma, they are parameters of these particular distribution, and given data I can always estimate from sample. I can infer the value of mean and standard deviation, and these are the two parameters that I need to fully characterize the behavior of fx, because if you recall, fx depends upon mu and sigma as only two variables, and pi remains constant, and all others, 2's and squares, are just mathematical notations that become part of fx. So given mu and sigma, I can, and for different values of x, I can fully characterize or plot this particular behavior of fx. So it is 2-parameter distribution. Now, if you recall from our last discussion, when we talked about PDFs and CDFs, we learned that given a PDF, if we have PDF, and if we integrate PDF up to point of interest, let us say -infinity to x, we get another function, what we call as capital Fx, which is also CDF or cumulative distribution function. Now, interestingly, even if we know Fx now fully, we have to still integrate it, -infinity to x. Now, this particular function, while mathematically well defined, it cannot be integrated analytically. And that's where we need help of some functions called as Basel functions to do integration of these particular functions. Now, since we encounter these distributions so many times in engineering, sciences, and everywhere else, we have generated some standard tables to find this area under the curve or area under the curve to calculate values of fx. And that is where this term standard normal distribution comes into picture. For example, what may happen is that for different situations, let us say we talk about rainfall. We may have rainfall mean to be around 5 mm for given location. When we talk about floods, we may have mean flood level to be 5 feet. When we talk about number of cars crossing an intersection, we may have number of cars to be 1000 vehicles crossing a particular intersection per hour, and they are also going to have their own variances. We call as sigma a square, sigma b square, and sigma c square for three situations under discussion. Now, if every data that we encounter is going to have different mean and variance, we are not going to generate thousands of data sets, thousands of tables containing the calculations of probabilities. Hence, we introduce this concept of standard normal distribution, where we say that instead of dealing with x, we define another variable z, which is original variable minus mean divided by sigma. We subject each and every sample to same mathematical operation, that is x minus mu divided by sigma, as a result of which we get a new vector, z vector, containing our samples z1, z2, zn, which are same in number as our original vector or original sample size. But this particular time series or this particular series or this vector, we can sometimes call it time series, sometimes we call it vector or series itself, depending on the context. It will have mean equal to 0 and standard deviation or variance equal to 1. And we say that we have normalized the original vector into a standard normal distribution sample, assuming that original data was actually following normal distribution or original samples were coming from normal distribution. Now, with this mean 0 and variance 1, we don't need a number of series or tables, because whatever we do for 0 mean and 1 variance calculation, without altering the behavior of distribution, we can transform our original variables back, because we already know we subtracted mean from them and divided them by sigma. We can always multiply them by sigma and add mean to z variables to retrieve our original variable. So all at the end we need is one single table to do all our calculations around normal distributions. So the mathematical form now becomes, instead of f of x, we say it's f of z. Certain books or resources use notation f of s. S is in standard, but here we will be using notation of z to represent our standardized variable, where f of z is 1 by root 2 pi exponential minus 1 by 2 z square. If you notice here, sigma has disappeared. It has not really disappeared. It has taken value of 1. So we are implicitly assuming that it's there. Z is essentially x minus mu divided by sigma by definition, and hence entire term gets condensed into minus 1 by 2 z square. This revisited form retains all the property of normal distribution, that is, it is symmetrical, mean, mode, median are same, and whatever properties would apply to any mean and any standard deviation series or vector of samples, it will also apply to this particular probability density function. Since this is still a PDF, the definition of CDF would apply, where we will say that CDF of this is by definition probability of z less than equal to certain value or minus infinity to particular point of interest, and instead of fx we will integrate fz dz, and we will call this as our cumulative distribution function. And we can calculate that value of standard normal variate z at cumulative probability p as phi of zp equal to p. So if we know p, that is probability or cumulative probability up to that point, we can always calculate value of ZP by simply saying that ZP is nothing but inverse of P. That is, we can go from probability to calculate value of ZP. If we know the value of ZP and given normal distribution table, we can also calculate P. These things will become much more clearer when we will go to example and actual table, but it is important to familiarize ourselves with the notations because we may encounter these notations in any situation or circumstances. So again, to re-emphasize, standardization is a process to convert any normal distribution X to a standard normal distribution Z using a transformation Z equal to X minus mu by sigma. And these transformations are pretty standard operation in many mathematical and statistical operations that we do while dealing with random variables. Then instead of worrying about the integration from minus infinity to z or from minus infinity to infinity or any point of interest, we will use certain tables which are well established part of every standard textbook on probability and statistics. So we don't have to manually integrate every time whenever we have to solve a probability and statistics question. And also that negative values of z, for example, your z score comes out to be minus 0.5. That essentially means if this is 0, negative side would be on left side, and this by symmetry 0.5 would be at this same distance on right side of 0 as minus 0.5 would be on the left side. So if we know probability of z less than equal to some positive value of 0.5, it will be indicated by the green hatched region that I have just drawn. We know that area under PDF is equal to 1. Hence, I can always calculate this red area as 1 minus phi of 0.5, and this essentially is also probability of area that I just shaded now, because area that I have marked as A and B are equivalent. So I can always write that probability of z less than equal to minus z is equal to 1 minus probability z less than equal to z. That means even if I have access to half of the table, I can apply this simple mathematical operation to get all probabilities at any point in my calculation. Now, this is one typical standard normal distribution table which says that at z equal to 0, area is 0.5. And if I draw the associated bell curve with this particular table, it should take a form in such a way that if my x-axis has z, my y-axis will have values associated with pz, and my normal distribution is now standardized, and hence it is centered around z equal to 0. And at z equal to 0, table shows the value of 0.5. That means this is the red area that this is talking about, and this area is equal to 0.5 for the first entry. Now, if for example, if I go to z equal to 0.1, if z equal to 0 is here, z equal to 0.1 would be on right side of z equal to 0. And if I now draw this particular area by blue color, this area is 0.5398. That is away from the mean, I have added another 0.0398 to the area on left side. So it becomes 0.5, which was already around the center, plus 0.0398. Now it makes sense because if you recall, definition of median was area up to x. Wherever area up to x is 0.5, that value of x is median. We already learned that normal distribution has same mean as median. Now we already said that mean of this standardized normal distribution is 0, and hence area comes out to be 0.5. And this particular table has the first entry as 0.5. So we have to really understand this particular figure and this table. And this table is nothing special. It's just the integration of the function, that exponential function that we saw, and it makes our life easier if we can visualize these particular elements clearly. And this would be used very frequently whenever we'll talk about calculations around normal distribution. Now let us try to understand this with help of an example. Let us consider a mean flood level of 5 feet and its variance is 1.5 feet. If you recall, when we introduced first example in module 2.1, there also flood level was 5 feet. So we will be sticking around same numbers and we'll try to make maximum sense by end of this course to solve really complicated examples. But the foundation stone remains here, even with the same numbers and example coming again and again. We are asked a question: calculate the probability that flood level exceeds 6 feet in a given year. Now, it is a non-linear function. If you would have asked me, calculate the probability given that flood level exceeds 5 feet, I would have immediately said it's 50% chance. Why? Because mean is 5 feet. On either side, it would be 0.5 area. Hence, probability it would exceed 5 feet is going to be 0.5. However, from 5 to 6, it is not decaying linearly. It is decaying exponentially. Hence, my intuition would not apply. Just by interpolating, I would not be able to answer it because exponential functions will decay much, much faster. Hence, I have to use tables rather than testing my intuition here that if I know 5, I should know answer for 6 and so on. So first of all, we'll calculate the standard deviation, which is square root of variance. 1.5 gives us 1.225 feet as its standard deviation. Now we know standard deviation and we know mean. And we also know that X under discussion here is 6 feet of flood. Mathematically speaking, we are interested in probability of X greater than equal to 6. As it says, calculate the probability that the flood level exceeds 6 feet in a given year. Sometimes you can also argue that isn't it probability of X greater than 6? Yes, but again using PDFs, we cannot determine the point probability. So answers would be very close to each other in practical world, even if we are considering greater than equal to or greater than as a same sign. Again, first step here is you see that mean is not equal to 0. Variance is not equal to 1. What we have to do? We have to standardize our random variable X. Standardized value of random variable X comes out to be 6 minus 5 divided by 1.225, which is approximately 0.816. Now, immediately what I would do is that I will draw the bell curve for this normal distribution. I will mark mean as 0 and now Z value is 0.816, 0.816. And in question it is asked probability of X greater than equal to 6. I will immediately highlight area of interest, which is purple in this particular case. Now, the table I have, I will look for 0.816 wherever it will lie. 0.81 has the value approximately 0.790. 0.790 and at 0.82 value that we know is 0.7939. So we can assume that at 0.816 value would be somewhere 0.792. What this 0.792 represent? It represents that area on left side up to this point out of 1 is 0.792. Total area under the curve is 1. If I know this particular area that I just hatched, I can easily deduce that purple area is going to be 1 minus 0.792, and that indeed is my probability of x greater than equal to 6, which is analogous to probability of z greater than equal to 0.816. Hence, we get an answer of approximately 20% of exceedance, that the probability that flood level will exceed 6 feet is 0.2061, all deduced from the Z table or normal distribution table in this particular case. So we have skipped entire integration just by using a table effectively, understanding that how that table relates to a normal distribution curve, and also then emphasizing which particular area we are interested in. So moving ahead, there is another important distribution that we frequently encounter in discussion around risk and decision making, which is exponential distribution. Equations and parameters we will discuss now. So normal distribution, for example, was a bi-parameter distribution. We needed mean and variance to fully characterize normal distribution. On the other hand, exponential distribution is uni-parameter distribution. You only need lambda as one of the parameters, and lambda relates to mean as 1 by mu in this particular case. So if you are confused, what is this parameter estimation? There are separate approaches like maximum likelihood estimate or other statistical approaches to calculate values of these parameters. But right now, that is not our primary concern. We will work with the data that is given to us, because our objective is to quantify risk. And we will assume that these parameters have been estimated for us from the data sets or observations or samples that have been collected from various sources. So we will go with that particular prior information. Here the functional form changes. Here, but interestingly, this is still an exponentially decaying distribution. This is also a thin-tailed distribution, similar to our normal distribution, but this is neither symmetrical, and more often than not, its mean is not equal to median. And also it would have highest concentration around the value of mean, but it would be slightly skewed towards left if we are talking about, and it is also function that takes form of monotonically decreasing function. So unlike normal distribution, it would have certain different properties, but still it's an fx under consideration. Whatever treatment we are going to give to any function in x, same applies to exponential distribution. So I would not worry about assumptions, presumptions about shape and form of this particular distribution. And cumulative distribution function, which again is minus infinity to x fx dx of this distribution, after integration comes out to be 1 minus e to the power minus lambda x, and this is defined only for values greater than 0, unlike normal distribution, which was defined throughout. And as you can see from the functional form of this distribution, it is fairly easy to integrate. Hence, whenever we deal with exponential distributions, we don't necessarily need the tables like we needed for normal distribution to do our calculation, and we will make it clearer when we go for example. As I said, mean of this distribution is 1 by lambda. So expectation is Ex 1 by lambda, and parameter of this distribution in this case is lambda, and variance and mean of this particular distribution are also related to single number lambda. And I leave this particular small part as a homework, that if mean of any exponential distribution is 1 by lambda, what would be its variance, and you can now also derive this based on the discussions that we have already had. But again, This is a single parameter distribution. We would not be using value of variance to do our numericals here. Let us go back to a same example. Mean level of flood is 5 feet. I have not said anything about the variance here because first of all, variance is related to mean in case of exponential distribution if you have found answer to the previous question. And also, I would not be using it throughout the calculation. Since mean flood level is 5 feet, lambda in this case is 1 by Ex. For mean flood of 5 feet, we get lambda is equal to 1 by 5 or 0.2 per feet. Probability distribution function in this case is given by lambda e to the power minus lambda x. Since lambda is equal to 0.2, we substitute lambda wherever we have to, and we get fx as 0.2 e to the power minus 0.2x. And when we plot this particular exponential distribution for lambda for lambda equal to 1 by 5, we get an exponentially decaying function. And again, if we ask question of interest that what is the probability that flood level will exceed 6 feet, we are essentially interested in the area that I just hatched now. So this is the probability of x greater than equal to 6. This particular area is probability of x less than equal to 6, and sum total of these two numbers again comes out to be 1. So if I do integration on either side, I can subtract it from 1 and get answer or areas of interest that are applicable for me. So same question again, and this again is the same problem of the coffer dam, but again we are building it in parts by parts that we'll put together in context of a bigger, broader engineering problem. So when we talk about probability of x greater than x, it simply becomes 1 minus f of x at 6, because cumulative distribution is on the left side. We are interested on right side area, and hence it becomes 1 minus area on the left side, and area on the left side is essentially CDF or cumulative distribution function. In this case, we know from our discussion that for an exponential distribution, cumulative distribution function f of x is given as 1 minus e to the power minus lambda x. So we'll simply substitute the values and get value of f of 6, capital F of 6, as 1 minus e to the power minus 0.2 times 6, and hence it comes out to be 0.6988. And we are interested in, this is the value of probability x less than equal to 6. Since we are interested in probability x greater than 6, it becomes 1 minus 0.6988 or 0.3012, or there are 30% chances that flood level will exceed 6 feet. Two things to notice. It's the same problem, same mean flood level that we are talking about. When we used normal distribution, we got flood probability as 20%. When we used exponential distribution, we got flood probability as 30%. Which one is right, which one is wrong? Mathematically, both of them are correct, but there are different steps that we use to actually determine whether samples are indeed coming from following normal distribution or exponential distribution, and we typically use a measure called as goodness of fit in statistics to really determine which particular distribution to use or not. Because if choice of distribution is incorrect, that means your samples or population is not following a particular distribution, and you wrongly infer or use a preconceived form of a function, your estimates of probability are going to be wrong or differ in magnitude. Like 20% and 30% are significantly different numbers, and hence magnitude of risks are also going to be wrong or different if choice of distribution is not correct. Hence this goodness of fit becomes an important aspect in probability and statistics. But again, in this case, we will stick to that given the particular form of distribution, how to deal with that. But I strongly encourage that if you are interested, you should read a bit about hypothesis testing and goodness of fit, how to choose or infer a particular distribution given different samples. Now, let us relate it back to our cofferdam example uh, and modify this question slightly. Now, we say that given mean flood level is 5 feet and the flood levels follow an exponential distribution, if flood height exceeds 6 feet, the damage is going to be $25,000. Calculate the expected loss due to flood damage. Now, we are now talking about expected costs. And we know that cost is going to be 25,000 only when flood level exceeds 6 feet. That means we are interested into integration from 6 to infinity, fx dx. This 6 to infinity can also be written as 1 minus infinity to 6 fx dx, because total area under the curve from minus infinity to infinity is equal to 1. So if we are interested in 6 to infinity, we can go from minus infinity to 6 and subtract it from 1. And this form is nothing but CDF, or cumulative distribution function. So the point is that if our fundamental is clear how to relate PDF to CDF to probabilities of accidents, we can calculate any risk or any estimates if the underlying distribution is clear to us. In this case, it simply becomes probability of X greater than 6 multiplied by damage. Our damage in this case was around 25,000, and we already determined that probability of X greater than equal to 6, given that X follows exponential distribution, to be around 30%. And hence this around, you can do this particular math, but this is what is our dollar value or the expected losses associated when flood exceeds 6 feet. And you can draw a rough analogy to an insurance world, right? If I have to insure or pay premium for a particular infrastructure, the total damages may be 25,000 units. However, if probability of things going wrong is very, very, very low, I should not be paying the insurance premium as high as the asset value itself. It is always the product of the asset value multiplied by probability of things going wrong. If probability of things going wrong is very, very low and asset value is high, the value would come out to be in a moderate range. A classic example is a vehicle insurance or a car insurance. For example, a typical car may cost 15 lakh rupees. However, we end up paying 10 to 15,000 rupees per year as an insurance premium. And the fact is that because insurance companies would calculate that based on the data or based on the claims that they have settled, what is the probability for a particular driver to get into an accident, and given an accident, how much damages a typical company has to pay, and based on number of policies they sell, what is a optimal policy value, so that company is still able to make a profit while retaining the customers, or giving enough encouragement to customers to protect their assets at values much lower than the particular asset value. The reason we are mentioning that, because these two distributions opened entire avenue for us to quantify risks associated, because risk is typically expressed in dollar value or rupee value, and that's exactly what we did using these two simple distributions, that is normal distribution and exponential distribution, that we really quantified risk associated with the flood of certain magnitude. And now doesn't matter what kind of functional form this fx takes or cost takes, we can always calculate the total losses associated. So this is all about continuous distributions. In our next discussion, we will move on to their counterparts in discrete world, and we will touch upon two most important discrete distributions as we go forward. Thank you.